so in our last meeting, if you recall, we started discussing complexity of a circuit. Okay? Okay, complexity of a circuit was based on three different metrics, if you remember. One of them was the number of letters or variables in a given Boolean function. The second one was the number of inputs, of a given gate. For instance, 2-input gate counts 2. 3-input gate counts 3. Okay? And we have another one, which was gate number of inputs plus the number of NOT gates, negations. Okay? And we actually called them V, G, and Gn, if you remember. Okay? And we will compare circuits most of the time based on these metrics. If one of these is bigger than the other, then we call the lowest G circuit, achieving that G, is low complexity. Okay? So let me give you an example just to refresh your mind that we have already learned in our last online meeting. Okay? So here's an example. We have 3 inputs, A, and we have... Today's subject is quite exciting, not this one. After that, I'll start discussing Karnough maps, which is just like a puzzle, but we're trying to optimize the Boolean expression. In other words, minimizing a given expanded Boolean expression to get a simpler function so that we will use only few gates to implement that. Okay? So that part is exciting to me. I hope that it's going to be exciting to you. Alright, so we have A, we have B, and an AND gate. We have another AND gate here, which is 3 inputs. So this goes here. And there's an OR gate here. And these are, of course, connected, right? And that goes here. There is a C. That C also goes here. And I have A also that goes in here. And C has a NOT gate, and that goes in here. Okay, finally, we have these 3 outputs all together. Okay, so you're given this output. You are given this logic diagram. Okay, there might be multiple ways of asking different questions for this particular logic diagram, such as, what is the output, for example, Boolean expression that should be expressed in terms of A, B, C, for example. Or draw the truth table corresponding to this logic circuit. That might be another interesting question. The other question, for example, write the SOP or POS form of outputs, for example. Okay, these are standard questions. There's no trick in it. Okay? Just straightforward questions. Answers are also straightforward. The background you developed so far should be sufficient to answer those questions. Okay? Alright, so one of the things that I'd like to do, of course, with this one, with this logic diagram, is to calculate the complexity. In terms of the complexity metrics we are already familiar with. Variable, G, number of gate inputs, and Gn, number of gate inputs plus NOT gates. Okay, could you please tell me, what is V? In order to answer this question, what should we do first?
Number of variables.
Number of variables, but the answer is? Can you tell me the answer?
3.
What's the number of variables?
3.
What?
3.
3? Yes, I mean there are 3 inputs that goes into the circuit, but when we calculate V, we look at the output Boolean expression. Okay, we have to first calculate the Boolean expression that corresponds to the output, given that are these A, B, C 3 inputs. Okay? So the answer to that question is not 3. Okay? We have to calculate the output first. Can you calculate the output online right now and tell me?
7.
Okay, you say, what's your name? Jamila. Pelin. Okay, because of the mask. Okay. Pelin says 7, right? Says 7. Okay. Jamila is another beautiful name, by the way. I love it. Go ahead, Tom.
Also 7.
You say 7? Okay, Sean also agrees with 7. Can you please first tell me what the output is? That the Boolean expression of output? Anybody who might want to volunteer?
I have also another answer. 5.
5. What's your name?
Ahmed.
Ahmed says 5. Okay, anybody else? Come on guys, you have to first calculate the Boolean expression that corresponds to output. And I've shown you that. You have to walk through these wires. Okay, write the Boolean expressions right here and then here. You should be able to get the Boolean expression pretty quickly.
Yep.
Should we count the same variables?
Well, there is a method to calculate V that I talked about in our last online meeting. So let's just wait until the end, so you probably will get your answer. Well, in order for it to be 7, yeah, you have to count A, B, and C multiple times. Or their complements. Anybody? Can you tell me the Boolean expression for output? Okay? Want to volunteer? Want to be volunteer? Okay, say it.
A prime B
A prime B
plus ABC
plus ABC
plus A
plus
B
B. Just B?
plus C prime plus C prime.
And plus C prime.
Yes.
Okay. Do you agree with that?
Yes.
Yes.
Everybody?
Yes.
There are anyone who objects to that answer? No? Okay, let's just walk through it. I know that it's simple, but for those of you who I might have lost, through the way. So I want to just go through it together. Okay? This is A prime, right? This is B. So what is this? A prime B. Okay? So as a convention, I usually use A prime in the first place, and then B prime in the second place, and then C prime in the third place. Okay, just a convention. Okay, so here I have B, so this is B. This is what? A. This is C. So what is that? A, B, C. Okay? Alright, how about this one? B. Okay? This is C prime. Right? So we got B, C prime.
No. B plus. It's all.
I've actually made 2 errors. B plus C prime. Correct? Everybody agree? Alright. So then, this is an OR gate that ORs A prime B, A, B, C, B, and C prime. Okay, everybody agree with that, I guess? Alright? Okay. So now the answer is 1, 2, 3, 4, 5, 6, and 7. Okay? Question?
B and L are the same thing, right? Or we can also call
Yes,
it L.
right, literal. L means literal. And that exactly is identical to variable. Okay? Alright, everybody agree? Okay, good. So, this is our first answer. So, the other answer is the question, actually. The second question is G. What is G? And it says 10. 10? Anybody who doesn't feel like it's 10? No? Okay, by just looking at this expression, or you can count if you want, because it's just much easier because it's an illustration of the figure. All you have to do is just count the inputs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or if you don't want to draw the logic diagram, then you should be able to figure this out from the Boolean expression. 2 here, 3 here. Well, there is no gate here, and there is no gate here, right? So 2, 3 makes it 5. So this actually corresponds to, this is an OR gate, so this actually counts 2. Of course, 2, 3, and 2. And there is an OR gate that connects these, right? Or you can go ahead and do the following. 2, 3, and then there is a 4, 4 input, 1, 2, 3, 4 input OR gate. That will also give you the same answer. All right. So you can think of, well, our answer is based on this circuit, or if you could, you can actually draw the following. If you let me to erase some part of the answer. So let me just give you the following variation. Okay. So let me just erase this. Okay. And connect the following dots, just to show you something interesting. So this goes here, and that goes here. That also is the same, right?
Yes.
Because we're just ORing. Okay? So now, instead of counting the inputs here, for example, were counted 2. Okay? Now it's right here. How about one of the inputs of this OR gate? It's gone, right? That means this one, that one, and the other one that was the output of the OR now is disappeared. Okay? Which means if you count the number of inputs now, 1, 2, 3, 4, 5, 6, 7, 8, and 9. G becomes 9 now if you use such a configuration. Okay? So what's happening here? Is it really true that if we collect all, inputs under multiple inputs, OR gates or AND gates, would that be something preferable? In fact, we didn't really think about the complexity inside of that gate. If the number of inputs increase, the complexity here is not linearly increasing, most of the time quadratically increasing. So which means that this would be, in general, in practice, more complex. Okay? However, of course, our metric does not account for that. So which means this gives us, for example, 10. Actually, it does account for somehow. Okay, so for example, G is 10 here and G is 9 here for this particular configuration, which means this is less complex. When I said it doesn't account for that, is that we didn't consider what's inside. In other words, we think that if the number of inputs increases, we assume the complexity of manufacturing such a gate is linearly increasing with the number of inputs. But that's rarely the case, in general, in practice. Okay? Just keep that in mind, but so long as the context of this class is concerned, we will be always assuming that there is a linear relationship between the gate complexity and the number of inputs, all right? This is just a metric that quantifies that, okay? We may be coming up with another metric that would actually describe the real phenomena better, maybe. But for this particular case, you will assume that so. Anyway, final question, what is Gn? For this particular, let's just focus on that one. Okay, so let's just erase this part and go with G equal to 9. How about Gn?
11.
11, right? Because there are 2 NOT gates, you can see. Or from here, you can see 2 NOT gates. Okay, any question? Now,
If we have one more A prime, would it be 12 or not?
where?
Plus A prime.
A prime, okay.
It is still.
Well, you will actually get this A prime here, and then put it here.
Yes, so 11.
So that would give you one more G, right? Your G now increases from 9 to 10. That makes 12. Okay?
If we add another inverse gate, for example,
Where?
Anywhere.
Okay, then you will have to increment that one.
Okay.
Okay? But
So the Boolean expression with the first and second,
I can't really hear you.
the Boolean expressions are the same with the first and second diagrams, right? The positive.
This one is a Boolean expression, yes?
It's the same with the OR gate and not with the OR gate. That alternative
Yes.
with the OR gate, right?
Yes.
What if we first see the Boolean expression and we try to draw this diagram, and I will actually draw it with the OR gate, but I will be wrong with the G.
Correct.
So how would I do it now?
That's a good question, perfect question. So that's why when we say this G, G, and V, did you understand your friend's question? He basically says that you can draw multiple circuits here that would map to the same V, G, G, N. Right? That's practically what you mean. So which circuit we're talking about by just looking at the Boolean expression, we cannot identify. which logic circuit we're talking about. So that's a great question actually. And of course, if you don't draw your logic diagram, that would be one of the confusions that you will have. So in the exam, when I ask you such a question, okay, if there is only one way of drawing this Boolean expression, then don't bother. Just calculate it, do it. But if there are multiple ways, then draw your own circuit, then calculate these G, V, and Gn. Okay?
So we did use certain pattern anyway.
Say again?
We need certain pattern anyway.
You need this, yes. Because these are defined for the circuit, not the Boolean expression. I was just being sloppy when I say, just look at the Boolean expression and calculate it. That's a sloppy expression. Right. Because we're talking about the logic diagram rather than the Boolean expression. These are not defined for the Boolean expression. Alright? Perfect question. Okay, so let me move on to the main genre of today's topic, which is the Karnough maps. Okay? Alright, so let me just briefly talk about the Karnough maps because, as I said before, SOP and POS. Okay, so we have, for instance, a simplified Boolean expression. Okay? A simplified Boolean expression, and we have SOP or POS forms. These are the expanded version of the simplified Boolean expression. So we know how to go from here to here. And there's a one-to-one relationship between the SOP and POS form and truth table. Right? Truth table and SOP POS form. There's a one-to-one relationship. Right? Remember? Mean term, max term? Okay, perfect. So, and of course there is the logic diagram that you learned now, right? That you can draw a logic diagram from the truth table, or from the SOP POS form, or from the simplified Boolean expression. So there's this connection that you can go back and forth, and there are multiple ways of drawing the logic diagram, as you have seen. Okay? And one of the main objectives when you draw the logic diagram is to minimize one of these, G or Gn. Okay? One of the objectives. However, we didn't talk about just yet, going from here to here. Somebody gives you the truth table or SOP POS form, same thing. Then you go from here to simplified Boolean expression. How are we going to simplify it? Because if you simplify it, that's maybe one of the best steps you can take in order to minimize these G and Gn metrics. Okay? So I'm going to talk about today how we'll migrate from this context from SOP POS to simplified Boolean expression. Okay? Or for the same matter, this one. Okay? Because there's a one-to-one relationship between these two sets. Okay? This is the general view of what we're trying to accomplish today. Okay, now, optimization. So here I'm going to talk about, of course, K-maps, right? K-maps. This is Karnough maps. This is one of the many methods to optimize the Boolean expression or simplify the Boolean expression, all right? There are other methods as well. But I'm going to focusing on this one because it looks like a puzzle, so it's easier to understand, and it's, I think, more enjoyable and entertaining for students to deal with, okay? All right, a K-map consists of square cells. So we're going to be drawing lots of squares. Each cell represents a particular mean term, all right? Collections of these cells represent a Boolean function, okay, which I'll show you in a minute. And the mean terms in the adjacent cells differ in the value of one single variable. Remember the gray coding? It's just like that. Okay, there's only one bit changing between the adjacent cells, and there's a specific reason of why we're doing that way. And K-maps can be used in any area where complicated Boolean conditions are heavily used, such as software. In software, we have conditional statements. You can actually apply the same idea, the Karnough map idea, to the software as well. This is hardware though. Okay, so let me give you an example of a simple K-map. For example, let's suppose we have the following truth table, right, and an F function. Okay? So let's suppose these are all the possibilities, and this is my function, 0, 1, 0, 1. It's just an example function. Okay? And mean terms, so let's just say mean terms. And I'm going to, of course, use my shorthand notation for the mean terms, M0, M1, M2, and M3. Alright? Everybody happy? You already know what M0 is. Can you tell me what M0 is, just to refresh what we have already learned?
X prime, Y.
X prime, Y prime. Absolutely. Okay? And how about M3? Somebody else? XY. Right? Okay, beautiful. Now, in order to, so this is one special way of representing mean terms. And I'm going to now show you another way, which is now using 2 dimensions, and that is called the Karnough map. Okay, so here we start like this, and then we divide this big square into 4 equal sized squares. These are cells now. Okay, and one of them, let's suppose that this direction, vertical direction, that's why I put X here. This is X equal to 0 row, and that's X equal to 1 row. Okay, and this is Y equal to 0 column, and Y equals to 1 column, and that's Y. Okay, now, in order to represent this function, f, for example, we know that m1 is 1, m0 is 0, m2 is 0, and m3 is 1. Okay? And m0 corresponds to x equal to 0, y equal to 0. In other words, x equal to 0, y equal to 0 here, that means this is my m0. Okay? X equal to 0, y equals 1, it's m1 here, m2 is here, m3 is here. Okay? Now, of course, instead of writing these m's, for a given function, I know what those m's are, right? For example, from the truth table, you can immediately realize that m0 is 0. So I'm going to put here 0. m1 is 1. If you're unable to follow, please interrupt me anytime. This is 1. m2 is 0. 0. And m3 is 1. 1. Okay? This is, as I said before, is just another way of expressing exactly the same thing. Exactly the same thing. Okay? And you will probably ask me, why do we bother? Why do we bother expressing the same thing in another illustration or formulation just like that? Just like this one. Okay, so the answer to that question is, I'm going to use another color. So let me use another color, perhaps red. Because now we are able to group things. For example, I'm going to group like this. Okay? Only the groups of size power of 2, okay, is allowed in this grouping. So you can group, for example, 2 to the 0, which is 1. You can have a group of 1, or 2 to the 1, group of 2, group of 4, or group of, let's say, 8, blah, 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 blah. Only those sizes are allowed in this kind of stuff. And there is no, diagonal selections. These are not allowed as well. You can only group things in vertical direction or horizontal direction. Okay? That's another rule. All right? So here, for example, you start with the, I'm going to, of course, talk about more formally how this optimization is done. But let's just focus on this one. And I actually figured out that there is a group of 2 here. As you can see, I'm grouping ones, by the way, mean terms. Okay, that are 1. Mean terms that are 1. So this is one group, one special group. And the rest of them are just 0. So what I'm going to say that this corresponds to a Boolean expression. What is this Boolean expression that corresponds to this? Okay, there's an easy way. In fact, so let me just write it down for you. This one is x prime y, and that one is xy prime, right? So f is actually equal to m1 plus m3, right? What is m1? X prime y. And what is m3? xy. Naturally, you would approach to this problem by using distribution law, right? By just taking y out, and there is an x prime x. But you know that x prime x is what? 1. So this is y multiplied by 1, or and with 1. So if you add things with 1, you get y itself, right? Okay. So this is the way we approach things to simplify. Since this function is quite easy to deal with, that's why the expression is pretty simple to express. However, if you look at this graph, you will realize that this group, okay, would correspond to y, Boolean expression y. Why? Because you see x equals 0 and x equal to 1, that corresponds to these ones. If you look at the row-wise and column-wise, if things are already covered by 0 and 1, you basically eliminate that variable in this formulation. In other words, you eliminate x completely because x equal to 0 and x equal to 1 is accounted for by this grouping. And y is not, because there is no y equal to 0 case here. So think about the following big group. If these zeros were 1, you got 1, 1, 1, 1, right? So you would get this entire table as a one big group. In that case, you will realize that x equal to 0 and x equal to 1 are accounted for by that group, as well as y equal to 0 and y equal to 1 are also accounted for. So in that case, you will see that both x and y are gone, so you get only 1. Okay? So that's why this technique, which I'm going to formally introduce in a minute, will help us to deal with larger Boolean expressions, because this is only 2-input case. In the case of 5 inputs, for example, it will help us tremendously to do the minimization, because we won't be able to figure out these simplifications in a larger input scenario. All right? So this, for example, corresponds to y. You see, all these calculations are not done here, because it's just this actually corresponds to y, simply. So let me draw the same diagram, but of course I'm not going to write, when I draw the Karnough map from now on, I'm not going to write it, explicitly just like that. What I'm going to do is I'll put x and y on top and put 0 here, 1 here, and 0 and 1 here to mean it to exactly this diagram. Okay? So in this case, let me give you another example. Let's just put 1, 1 here and 0, 0 here. And I'm going to group these two ones. And what is the Boolean expression that corresponds to that group? X, right? Because y is now covered by this group, and x equal to 0 is not. So the question is this x or x prime?
Prime.
It is x prime. I am actually assuming that you are doing at the background such a calculation to verify that it's x prime. If you go through this formulation like that, using distribution note, you will realize that you can actually convince yourself that it's x prime. But why this is as x prime and why this is y? The answer is pretty simple. This group corresponds to x equal to 0. And we know that when things are 0, we actually complement them. This here is y equals 1. And since y equals 1, you write the y directly without complementing it. Okay? That's the difference between the two. Or let's just give another example, just to make sure that you understand this thing in the simple case. This is a simple case, remember, only 2 inputs. Okay? So let's suppose that these are zeros, and I have 1 here and 1 here. So what does this group correspond to?
X.
X, right? Great. Okay. How about I also change this 0 to 1? All right? And of course, I have to group things such that there are no ones left out. So, can I do this? No, because this is not a valid grouping. In my valid grouping, I have to comply with the rules of the grouping. Okay? 3 cannot. And also, I cannot do diagonal groupings. So there is only one way to cover this one. This one. Okay? You could say that, this one is accounted for by 2 times. That's fine, because there is no other way. Okay? So this group corresponds to x. How about this group? This is y. We already done that. So the answer is f. Let's say f2, because this is my f. I don't want to confuse it with the other f. So f2 is another function, Boolean function, corresponds to x plus y. This is the simplified version of f. What's the not simplified or non-simplified version of f2? Let's just write. Okay? So this, for example, corresponds to 0, 1. So this mean term, and this mean term. okay? Which means M1, M2, and M3, which is more complicated than this one. But this is a simplified version. All right? Okay, so this is a brief, of course, introduction to Karnough maps. Particularly, things get more excited when you think about 3 inputs or 4 input cases. All right? So let me just also give you the example of 3 input, and I will probably go over a 4 input scenario in my examples, further examples. And I will leave 5 input and 6 inputs to your imagination. All right, so let me give you a 3 input case. Okay. So let me ask you this. In the 3 input case, how many cells do I have? 8, right? Because in two cases we have got 4 min terms, right? Think about the truth table. And if you've got 3 inputs, that means that you've got 8 min terms. And each cell corresponds to a single min term, okay? So there are 8 cells, but how should I structure that 8 cells? How should it look like? Can I use, for example, the following? 4 here, 1 here, another here,
No.
okay, and then maybe 2 here. Huh? How does this look? No? So what you should expect then? What's your expectation? I want you to use, because, you know, it's always okay to guess things, you know, because it will add up to your intuition on our way to the destination. I don't expect you to give me the right answer, okay? I want you to give me an answer. Okay, so what's your expectation? What should it look like?
It should look like a chessboard.
Chessboard. But we have 8 cells. So in chessboard, it's square. So what should you expect? Because I cannot put 8 cells into a square, right? Because these cells are all equal size.
I think table like 2 rows, 4 columns.
2 rows, 4 columns. Maybe. Yeah, let's just see.
Or 4 rows, 2 columns.
4 rows, 2 columns. Okay, let's see. Anybody else?
8 to 1.
Hmm?
You can create 2 truth tables, one with solutions and the other.
What do you mean by 2 truth tables?
Not truth tables, 2 K-maps.
K-maps, yes. Well, this is one particular way of drawing. There is one unique K-map, by the way. But the way that we present that K-map might be different. As your friend suggested, this is one way, and this is another way. Okay? And I'm asking if you have got another proposal. Yep.
And we have one extra column for full zeros
Like
at the end.
1 column,
Actually, 2 columns.
then this corresponds to this one, right? 2 columns,
Yeah.
4 rows.
We have 2 more columns to the right with full zeros. Make a difference
Why do you introduce zeros?
because
We have got 8 min terms, and we would like to place those min terms into 8 cells. We don't need zeros.
we need a square shape for it.
Oh yeah, you mean you're trying to make it square, but introducing zeros doesn't make any sense because there are no min terms in those places. So introducing extra min terms would not give us any, you know, advantage. 3 by 3 makes 9. So you've got 1 lingering cell. What are you going to do with that? There is no min term. There are only 8 min terms. Okay? So your friend suggested a similar thing. He said that let's just put 0 here, but it's not efficient. Because there is no expression that corresponds to that cell. So if that cell is to be used, for example, by another, then what are you going to do? You write to in that place. There is no Boolean expression.
If we give 0, we don't need to.
But adding, so it's inefficient, as I said. Putting a 0, doesn't make sense.
When we compare with that,
So let me answer. Another possibility would be 1 column, 8 rows, right? That's a possibility. Why not we just go with that? Okay? And similarly, 1 row, 8 columns. Agree with that? Yeah, that's another way. Okay? So, I mean, in fact, due to this rule, it has to be a power of 2, the groups as well as the big bucks, you know, the Karnough map itself has to be, the number of cells has to be powers of 2. So because of that constraint, these are the only ways you can actually go with. And unfortunately, there's no other way. Okay? But the question is which one we should select. In fact, one of the things we realize that these are actually identical to each other. It doesn't matter what you're looking, if you're looking from this direction or this direction, it will give us the same result. Okay? It turns out that way. And these two also the same. So question is, which one is preferable? Meaning that, which one I should use so that I can minimize my expression. In other words, if I use this one and minimize my Boolean expression and do the same thing with this one, this would give me, or this one give me, a simpler expression. So which one do you think would give us this simpler expression?
Left one.
You say left. Okay. So let's just vote for those of you who wants to vote. Who votes for the left one? Okay. All right. All right. Okay. How about right one? Okay. 2. Okay. 3. Okay. Okay. So answer is left one.
Oh.
I actually introduced this to convince you otherwise, you know, trying to get the votes to different direction. So it turns out that this gives us the simpler version, and there's a physical explanation to this. This shape here minimizes the entropy in a physical space, three-dimensional Euclidean space. So if you, for example, think about spheres, for instance, having millions of cells in them, okay? The way that they assume a sphere shape is because of minimization of entropy rule. Okay? Because those cells might be arranged in some other way so that they will assume different shapes. However, sphere minimizes that. And similarly, since there is a constraint, there are no infinitely many cells in this case, that's why this minimizes the entropy. For example, if I assume 16 cells, so you said that, for example, it has to be a square shape. Why? Because it minimizes the entropy. And that's the correct answer, by the way. It has to be 4 by 4, 16 cells arranged in a square shape. That is the answer. Because it minimizes the... So, if you have a 3-input case, in the 3-input case we will use this diagram. So let me erase the rest after having this beautiful discussion. Probably we will never visit this discussion anymore, but just keep this in mind. Things are aligning itself in space based on their entropy. And they try to minimize the entropy because of conservation of energy. Okay? Alright, so we have got 3 inputs now. I'm going to start with X here, and there are 2 more, so I'll put Y and Z here. Okay? Now remember the mean terms, M0, M1, M2, M3, M4, M5, and 6, M7. So I'm going to start writing these. This is 0, this is 1. I'll start 0, 0, 0, 1, 1, 0, 1, 1. Okay, hold on a minute. If I do this type of mapping, then if I look at these 2 neighbors, select this cell. If I go from this cell to this cell, okay, there are 2 bits different. Right? Because this cell corresponds to 0, 1, 0. How about this cell? This cell corresponds to 0, 0, 1. How about this cell? 0, 1, 1. So if you go from here to here, there's a 1-bit difference, which is actually in line with the definition of Karnough maps. It has to be 1-bit difference when you look at the neighbors. Neighbors meaning that these are not neighbors. I'm talking about the closest neighbors. So there are 3 neighbors here, and they have to differ only in 1 bit. Okay? So, the answer, so when you look at these 2, you will realize that there are 2-bit difference. Okay? So that is not desired in the Karnough map. Because the grouping that I shown you assumes that there is a 1-bit difference. That's why we have this kind of simplification. X and X prime goes away. because of that one bit difference. There is only one bit difference, and that difference creates this x prime type of simplification, or y prime or z prime, doesn't matter. Okay? That's the idea behind having neighbors differing in only one bit position. Okay? So, let's come back to our discussion. Instead of writing this way, I'm going to write the following way. I'm going to just write 1, 1 here and 1, 0 here. So I'll basically change their location. Okay? And you will now realize that the previous problem goes away. Select any cell and look at their neighbors. It will create only one bit difference. Okay? And that comes from our gray coding. Do you remember the gray coding? It's identical to this. Okay? For example, take this one. This corresponds to 101. How about this thing? This is 001. This is 100, and this is 111. Just look at their differences. There's only one bit difference between the neighboring ones. Okay? Any question? This is a one-time learning process. You learn this Karnough map, you will now know that you will draw the Karnough map this way. You're done. Okay? You don't have to think about it anymore because you know how to draw the initial map with zeros, with empty cells. Okay? So don't worry too much about it. Maybe I should ask you if I go to 4x4. Okay? In other words, 4 inputs. How about 4x4? I should write 0, 0, 0, 1, 1, 1, and 1, 0. How about row, the columns? 0, 0, 0, 1, 1, 1, 1, 0. Correct. If you write these by just flipping the last two, both in rows and columns, then you will actually get this property. Any cell and its neighbors differ only in one bit position. Okay? You can verify it if you like. If you don't believe me, just go ahead, verify it. Alright, great. Let's come back to here. Now, I'm going to write my minterms. M0, M1, M2. No.
3.
This is M3, right? 0, 1, 1. This is M2. Let's continue. M4, M5, M7. Right. M7 and M6. Let's write it here as well. M0, M1,
Four. 3.
M3, M4, M5, M6. What's the problem? This should be 2, right? 4, 5.
7.
Let's just M6 and M7. How about M8? Where is M8? Can you figure out? This one? That one. Perfect. This is M8, M9, M10.
M11.
Here? No, here, right? And M11, M12, M13, M14, M15. The way that from M6 to M7, sorry, from M7 to M8, this actually comes out because of the rows that we have interchanged. Okay? It should make sense to you, I believe. Okay, that's why we started M0, M1, M2, M3, M4, M5, M6, M7. Then I should have actually started here, but because the rows are interchanged, I start here. M8, M9, M10, 11, and then go back to here. M12, M13, M14, M15. Okay? You see, if you don't believe it, just look at M15. It's 1, 1, 1, 1. Makes sense. It's all 1. Okay? Okay, now we know where to put the minterms. Now, if somebody gives you the function f, right? This function, with 3 inputs this way, in this case, then you have got ones. For example, 3 ones. That corresponds to a specific set of minterms then what you have to do, go back to Karnough maps here, replace those mean terms that are 1 with 1, and the rest 0. But you don't need to put the zeros, just as a convention. Just leave those cells empty, okay? And only use ones, okay? So for example, let's look at this one because it's the most complex Karnough map on the board. So let's just look at this and erase all these M's. Of course, I'm going to know them by heart. And don't worry if you are unable to do that right now. But as you solve more and more questions, this actually now sticks to your mind, and you will know that map and all their mappings with the midterms by heart. So don't worry about too much. Worry about the, practical experience you lack at this point. Okay, so now I will put, for example, let's say 1 here, 1, 1, and 1. Okay? This would correspond to a function, a specific function that has got 4 mean terms. Okay? Let's say fx. Or maybe let's just use another function name, g, which I've never done that before. Okay? And I'd like to write the mean term SOP form of g. SOP form of g. Okay? So what is this? If you don't remember, so I'm going to give you a hint. Just start counting. N0, N1, N2, N3, N4, N5. Let's just write N5. N6, N7. Okay, N7. I'm fine. M8, N9, N10, and 11. So there's N10. Okay? You follow me? Okay, 11. 12, 13, 14, 15. Alright? That's it. You can also keep in mind their binary equivalents. For example, what is 5? 1, sorry, because it's 4-bit, right? 4 inputs. So this is 0, 1, 1, 0, I guess. Or maybe 0, 1. 0, 1. Sorry, 0, 1. So let's just keep the binaries also in our mind, because when I want you to write explicitly those mean terms, then you have to express them in terms of x, y, z, t or a, b, c, d. Okay? That's why I wanted to remind you that it's always a good idea to keep the binary equivalents in mind. 7, 0, 1, 1, 1. This is 1,
0.
0, 1, 0, I guess. Am I right?
Yes.
Okay? And this is 1, 1, 1. Okay. And if I want you to explicitly write it, then you have to go back here and let's just use A, B, C, D as our input literals. Then I'm going to use A prime B, C prime D plus A prime B, C, D plus A, B prime, C, D prime, and plus A, B, C, D. Okay? Are we good? SOP form. This corresponds to, in fact, well, I could have given you, in fact, not the table, but the expression. There's a one-to-one relationship, remember, between the Karnough map and the Boolean expression. So if there's a one-to-one relationship, then if I've given you this Boolean expression, then you should be able to draw this. Okay? By identifying M5, M7, M10, and 15, and put the appropriate locations, fill the appropriate locations with 1. Okay? Okay, now let's come back to our grouping, right? Because I've shown you the grouping for 2 bits, 2 inputs, but I haven't done that for larger input sets. So let me just get my, green color maybe. All right, so I'm going to talk about something very interesting about this, 4x4 Karnough map, so to speak. So if I would like to group ones, what should I do? I should first look for the biggest group I could have. Okay? The biggest, because bigger the group, the more potential for simplification. The bigger the group, more potential. Smaller groups actually gives you lengthier, bigger expressions. So you don't like those bigger expressions. I mean, in the limit, for example, take one of these. For example, this. What is the expression that corresponds to this group? This is a valid group, right? Because it's a size 1, which is 2 to the 0, so it's a valid group. Question?
Can you use a darker color?
Darker color. Okay, of course I can. Let me use back to black then. Okay. So this is a valid group because it is 2 to the 0. Size is 1, which is equal to 2 to the 0. So that's a valid group. So what is the Boolean expression that corresponds to this group? It is the mean term itself, right? The mean term that corresponds to x equals 1, 0, I'm sorry, xy equals 1, 0, or ab equals 1, 0, because I used ab, and cd equals 1, 0. So which is 1, 0, 1, 0, which one is that? Is this, yes, this is it. So which is that one? So which is actually a b prime, c d prime. So are there anything simplified here? No. There's nothing simplified. It's a long expression. So what's the need for Karnough math? That's why we're grouping things. Because as you have got bigger and bigger groups, you have got simpler and simpler expressions, Boolean expressions. So look at this, for example. The biggest group that you can ever come up with in this example, unfortunately, it's not a very lucky day for us, but we can actually group these two, right? And maybe these two. These are the biggest groups, actually, unfortunately. And how about this one? I cannot group like this, right? Because it's a diagonal, it's not allowed. And so that remains, unfortunately, like an orphan child. Okay? We cannot group this, it will stay as is. Okay, it's not going to be part of any bigger group. Okay, so that's the best you can do, actually, with this example. But let's just come up with another example. Okay, that would be more interesting and then give you or convey the idea better, I believe. So let me just draw things. Is red okay? Can you see red? Okay. Okay, so let me give you another example. This is very critical, okay? Just focus on this example. So let me just put ones and ones here. Okay? Okay. How about... Let's just put all. There are many ones in this case. You can see only 1, 2, 3, 4, 5 zeros. And the rest of the mean terms are all 1. Okay? Let's start grouping. Okay, what's the biggest group I could ever have? Group of 2? Of course. How about group of 4? Is that possible?
Yes.
Maybe here? Yes? How about group of 8?
No.
Would that be possible? Where is it? Group of 8. Again, group of 8, meaning that it cannot be, of course, diagonal, so it can only be a rectangle, right? Are there any group of 8 here? No. No. So group of 4 is good, so let's just start with group of 4. And we will start with bigger groups and increase the coverage area, okay, as much as possible. So, let's just start with this one. You see, this is a group. I'm going to actually call this, there is a specific name for that. This is a prime implicant, okay? Don't worry about the terminology too much, but when you read the book, I don't want you to get confused or shocked. Oh, there's a whole another bunch of names and terminology for this specific example. So that's why I'm going to also use the same terminology the book uses, but it's just grouping, nothing more. There's a prime implicant, okay? Well, let's just write prime implicant. Okay? Alright, so this is one group. Okay, so let's just consider another group. Just to make sure that all ones are covered. Okay, how about the next one? Can you tell me which one I should pick?
Last row.
Last row, this one? Yeah, maybe. Right, okay, good. Okay. What else? Are there any 4 group size of 4?
Yes.
Where is it? This one? Okay, beautiful. All right. Any more? Group of 4? No? All right. So I'm going to tell you that you are wrong, because there is also one more group of 4 here.
No.
of course, if you think about this map in 3 dimensions like a torus. This is actually a torus. We actually lay it down in 2 dimensions. This is a 3-dimensional object, guys. So let me draw the torus. It's just like symmetry. Okay? Excuse my drawing, but this is how it looks like. Okay? It's a 3-dimensional object, and we lay this on the surface of the torus. Okay? In other words, we got these. Okay? Interesting, right? So which means this boundary here is adjacent to this boundary. They're touching each other. Now fold it. Okay? And then this would actually create a circle, right? In 3 dimensions. And then put these circles together. Connect them. This would become a 3-dimensional object, which we call torus. Okay? We don't change the cells, by the way. It's still the same. Okay? You may come up and say that, oh, you would actually probably have to have extensions. You know, it's maybe some of the cells would be bigger and some of the cells smaller. Well, we're trying to make sure that they are almost equal size. I know that, you know, geometrically, it's impossible to put 2-dimensional, such a, you know, perfect square on the surface of a torus. It's impossible. Okay? But we just think about that way, because it basically makes it easier to think. These are adjacent, and these are also adjacent. Okay? Because of the 3-dimensional shape. So, if these are adjacent, then I'm going to directly assume that these ones are also adjacent to each other. Right? So, which means, actually I end up with grouping them. Right? This is another group, for example. It become a bit complicated, I know. But this is another group that maybe I can show this way. Okay? So this is also another big group because of that connection. Okay? So why did I do that? Because I'd like to cover these 2 left out bits, the left out ones. Okay? How about this one? How should I cover this one? There are multiple ways. For example, a single circle here, or maybe 2. But this one is a bigger one. You always prefer big ones. Because if you prefer big ones, you've got more simplifications. Okay? And less complexity in terms of V's, G's, and GM's. Alright? So that's why it's important that you group things like that. If there were a group of 8, then you should take that group in order to cover this one. Okay? In this case, this is the biggest group that you can ever find, okay, using the torus geometry. Okay, that's why we have a group of 4. Now we have covered everything in the table, right? We have covered this one with the biggest group possible, and the other ones as well, etc., etc. So we're done with the grouping. Okay. Then the rest of the calculations, we have to figure out what is the Boolean expression corresponding to this, Boolean expression corresponding to this, and that, right? So let me just, because it became a bit more complicated, so I'm going to draw it here. Alright? So let me give you a couple of examples to figure out those expressions easily. 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Let's suppose that this is AB, this is CD. You could actually start with CD in the bottom and AB on top. It doesn't matter. Okay? You will end up with the same Boolean expression anyway. Alright, so let me just give you an example. 1, 1, 1, 1. If I put those ones in the corners, you know that because of the torus shape, you can group them together. So this is a group. Okay, can you tell me the expression that corresponds to that group? Using the similar idea that I've shown you earlier. Look at the rows and columns. In the rows, you see this is 1, 0. And this is 0, 0. Which one is always 0? This one. Which one is that? B. The other vanishes. Because there is a 0 and there is a 1 for that particular literal. So A this goes away. Okay? So we have B prime because of the 0. Alright? So that's the first term. B prime How about the rows? I'm sorry, the columns. I've just done the rows. So the columns, there's 0, 0, and 1, 0. Which one is changing? C is changing. It goes away. Which one is not changing? D. And what is it? 0. That corresponds to D prime. You see the expression? There has got only 2 variables or literals that corresponds to this group of 4. In fact, if you've got group of 1, the expression that corresponds to that group would be 4 literals. If you got group of 2, 3 literals. If you've got group of 4, 2 literals. And if you've got group of 8, 1 single literal. Could be complement or itself. And if you've got 16, group of 16, the entire thing, okay, you got no literal, which means 1. You got only 1. Okay, because all the mean terms being 1 actually means everybody cancels each other out. So you actually get a 1 at the end. Okay? A function being equal to 1 may not make sense to you much, but this is a valid function. It always sends, whatever the inputs are, always sends it to 1. In other words, logical 1. In other words, true. Okay? Yes, please?
If this is a MUX variable, are we going to write fill the blocks with ones, right?
If you've got mean terms,
MUX.
yes, the cells are actually mean terms. So we fill the mean terms that are 1 in those cells.
If we are dealing with one terms, are we going to fill the other
Places with zeros, yes. If you have got a MUX term expression, then you fill the cells with zeros, then the rest will be 1, so you can actually know where the 1s are. You can apply the same logic. Okay? Go ahead.
Can you repeat the part that how did we get D prime, D prime?
D prime, okay. Let's just do it again. So you got this group. That group has got, it spans 2 rows and 2 columns. These are the 2 rows that's spanned by this group. So we look at the corresponding binary numbers. The first one is 0, the second is 0 for this row. And the first one is 1, the second one is 0 for this row. We immediately realize that the first bit changing, it goes from 0 to 1, 1 to 0. And that corresponds to A, because there's A and B. This actually means that A equals 0, B equals 0. Okay? This is just a shorthand notation. You remember here, I have got x equals 0, y equals 0, but instead I put 0, 1 here. Same here, if you've got 2 variables, one of them is the first bit, A corresponds to first bit, B corresponds to second bit. It's just shorthand notation. Okay? So which means A goes away. Because if you have got A equals 0 and A equals 1, this type of simplification happens. This one. Okay? That's why A prime plus A equals 1. That's why it goes away. Okay? And how about B? Well, B equals 0, B equals 0, so B stays. But you should not write B because B equals 0 in mean term terminology, it's a B prime or B complement. That's why we got B complement. And then and, because we're dealing with mean terms, that's why we got an and. Okay? And the columns. Do the same thing for the column. In the column case, you got 0, 1, and 0, 0. So that D is not changing, C is changing. C goes away. D is 0, meaning that's D prime. You put the D prime right next to the B prime. Is that sufficiently explanatory? Okay. All right. So actually, from now on, you should actually come up with, your own example and try to figure out the grouping and also the expression that corresponds to that grouping. For example, let me tell you, what does this group correspond to? Can you tell me? Crunch it in your own mind so we can verify that together. Okay. What is it?
BD.
What do you mean DD? BD. Sorry. Okay. What do you think? Is that correct? BD? Everybody agrees? Who's not agreeing with this answer? You're not. So what's your answer? What is D? Just D. But cannot be. This is group of 4, which means you have to have 2 literals.
Aynen.
So let's look at the row. In the row case, which one is disappearing? Which one is disappearing? Which is changing? A is changing, right? So A disappears. Which is left? B. But is it B or B complement? B itself, because it's 1. So there's B. How about columns? C goes away now, and D is left, because D is 1, so you put D. Alright? So BD is correct. Okay, how about the following? So let me read the row, because it gets complicated. So let me give you another example to show you. Okay, I'd like to group this. What's your suggestion? Group of 4? Group of 8? Is there any group of 8 here?
Yes.
Yes. Why? Because these are adjacent. So this is my group. Okay? May not look like a group, but in 3 dimensions it is. Okay, so what's the corresponding expression?
B prime.
Who says B prime?
B prime.
Okay, is that correct? What do you think B prime? Is that B prime? I didn't even write the rows, so let me just write it 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So let's look at rows. This is the row, right? And this is another row. And in columns, we got actually 4 of the columns, all of them. So which means, if you look at the columns, everybody changing. Right? You got all possibilities here. So that means C and D vanishes. Right? C and D vanishes altogether. There is no C and D left. Because we've got every possible combination of C and D. They cancel each other out. How about rows? What is not changing? B is not changing. A is changing. A goes away. So we got B is not changing. Is this B or B complement? You look at the corresponding bits, which is 0. That is B prime. Okay? Okay, so I'll keep adding 1s. So let me just add these 2 ones. I'd like to group it. How should I group? Group of 4, right? The 2. So we got this left. So what is the corresponding expression for this?
A prime D.
Say again.
A prime D.
A prime?
D.
D.
Yes.
D. Everybody agree? Everybody agrees? Okay. Now we got some kind of a channel between you and me. Beautiful. And let me just put one more 1, okay? Or maybe two ones. Let's just put two ones in here. Okay? How should I group this? Should I group like that?
4.
4, right? Because bigger the group, simpler the expression. So let me just get this group. Okay? Okay, what's the expression corresponding to this? What's that? C prime?
D
prime. D prime. Everybody agrees? Okay. Do I have to have, for example, this group or this group? Because these are also prime implicants. But we're not getting them because we already covered all the ones. You don't need them because that would create extra term in your one expression. You don't need it. Okay? So, for example, let me just clarify what I just said. This is also a prime implicant because it is valid. It is 2 by 2, 4, and it also. But we already have covered all the ones. This is a prime implicant, but this is not an essential prime implicant. Essential prime implicants are the ones that you need. Okay? So that's why this is not essential. In that way, I've actually defined another term, prime implicant and essential prime implicant. Essential prime implicants are the prime implicants that has got a 1 that is not covered by any other prime implicant. Okay? For example, this one is not essential. Why? Because look at this one. Is this covered by another prime implicant? Yes, this one. Is this covered by another prime implicant? Yes. Is this another prime? Yes, because this bigger one. How about this one? Is this covered by another prime implicant?
Yes.
Yes, it is. So this one is not an essential prime implicant. So you take it away. Do you remember the consensus theorem? In the consensus theorem, on the left-hand side, we got 3 terms. On the right, you got 2 terms. And one of the terms is just gone, right? That is exactly what's happening here. In that consensus term on the left-hand side, you got a term that is not even needed. It's one of these prime impotents, and it has to go away. And this is actually illustratively showing you that which one is necessary and which one is not necessary. John, question?
It's also proof of those questions, right?
Oh, fine. Yeah. So I haven't finished my discussion here. So my final word about this, because I need 10 minutes to start a little bit to give you information about MUXes, right? Because it's in the lab. So let me just give you some lab background for you. So my final word about this, as you have just done all these tricky puzzle-based, questionnaire, because this is like a puzzle question. So once you're done with the grouping and then figure out the expressions, the final thing you do, the function itself now equals C prime D prime plus A prime D and plus B prime. And this is the simplified version of this function that corresponds to these mean terms, okay? Which is a big expression, as you may guess, okay? And this is now connecting the dots here, okay? We're done with this, okay? SOP, POS, now we're able to go the simplified polynomial expression using Karnough map approach, okay? Of course, in order to develop a bit more experience with it, we'll probably solve a couple of more questions with the Karnough maps. Particularly, I haven't done that, but this is more complex. That's why I've solved the question using 4x4. But you can solve it, questions using 2x4 as well. And how about, for example, if you got 5 inputs? What's the Karnough map size? You would guess? 32. Yeah, there are 32 cells, but what's the shape? You cannot put 32 cells, equal size shapes, into a square, right?
For example, 8 4.
8 by 4. That minimizes the entropy. How about 2 by 16? It is possible, but it's not minimizing entropy, right? You have to make sure that rows and column numbers are closer to each other, right? I mean, as close as possible. And 4/8 is the best chance. Anyway, I think I'm able to give you, I hope, some basic understanding of what K-map is. There are many examples in the slides, by the way. You please take a look at them as well. So let me briefly talk about the MUX, okay? Just briefly, because all you need in the lab is simple 2x1 MUX. So MUX is a component that is under combinational circuits. Okay, it's a simple combinational circuit actually. Okay? So let me just give you this. MUX is shown this way. This is MUX. This is 2x1. So there are 2 inputs, A, B, and there is a select input, S, and this is output. What is select input? Select input actually means if select is set to 0, this is connected to the output. So it's like a switch. Okay? If S is selected to 0, it's set to 0, 0 volts for example. That A now appears at the output. If S is selected to be 1, then B is going to be reflected upon the output. Okay? And what's going to happen to A? A is open circuit. So it's just like a switch here. Okay? That connects either one of these wires to the output so that it would appear in the output. Okay? That is the functionality of MUX actually. Of course, you have to come up with the Boolean expression that corresponds to output. Okay? Which is pretty simple because let's just say F is the output. If A is appearing here, if S equal to 0, then I have to put S prime A. Okay? Because S prime is now 1, and 1 makes A to appear at the output. And if S equals 1 makes B appear at the output, then I have to put BS. Right? Now in that case, B is going to appear when S equal to 1. Because if S equal 1, S prime equals 0, that cancels it out. Okay? Does it make sense? So the Boolean expression is not complicated. Go ahead.
Are we going to use the enabler in this?
There is an enable in physical world, of course. Okay? But enabling is not too hard. In other words, if you'd like to add an enable here, for example, EN, then this is another input, by the way. Just put this EN and AND with the output. That's just that simple. Okay? Because if enable is 0, whatever that output is, AND will generate a 0. So it's not enabled. It's just, gone. If enable is 1, then this AND gate would just, let it go. That whatever that the other input is, it's going to appear at the output. Okay? Don't worry much about the enable. I know that it is part of the real circuits, but in the lab, that would be probably instructed to you. You should, for example, connect the enable to 5 volts so that your circuit will work, etc. But it's important that you understand the functionality of the MUX. Okay? One of the questions in the pre-lab, as I assume, that make, for example, an AND gate from a MUX. Okay? Can we do that? Of course you can. You just make sure that this looks like an AND gate. Okay? For example, you have a box, and there is an input A and B, and you have to use MUX or MUXes, maybe multiple MUXes, okay, to implement this specific function, such as F equals AB. It's an AND gate, right? I want to implement this function using a MUX. It also very is useful, by the way, to draw a truth table for MUX. So I think given the Boolean expression and all the backgrounds you have learned so far, I think you should be able to draw the truth table for this Boolean expression, right? Can I confirm that? Okay, please draw the truth table. There are 3 inputs and 1 output, F. Okay, so it's a row truth table. Just do it, you will realize you will actually gain lots of information about, implementing a MUX. Anyway, I'd like to implement this, and I need an AND gate. So I look at this expression and realize that there is an AND gate already inside this expression. Okay? So why don't we just put, instead of S here, let's just put A here. Okay? So designing the inside, I put A here, B here, and how about here? Okay? Well, let's see. I can put here, so I have to make sure that this expression, this here term, goes away, right? So if I put in place of A, I put 0, it goes away, right? Wipes away. So I put 0 here. Okay? So what did I get here? I get AB, which means I have an AND gate using a MUX. Okay? The way that I describe, this is of course simple, simple gates, AND gates. You can do the same thing with OR gates, or maybe let's just do a NOT gate. Because if I have AND gate and NOT gate, I have an OR gate using the Morgan's law, remember? So let's just make a NOT gate, okay? Negation, okay? Can you propose a solution for NOT gate? I want you to first, you attack the problem instead of I give you the answer. That way you've got a better understanding of what's going on. Okay, how should I do? What should I do to be able to implement a NOT gate? Do I have a NOT gate here? Come on. Before NOT gate, if I put instead of having if I put B here, what happens? Can you tell me? Instead of having a 0, let's just put B. What happens?
Nothing.
Would that change anything? Everybody can see that? It's not going to change anything. If you put the B here, this is B, S prime is B prime, right? I'm sorry, A prime. So it changes that, right? A prime. And this is, what is B? B is B. What is S? A. Okay, so what is this? This is not the same as AB, so it changes. So if I put instead of B, A, let's say put A, then you will have A. This is A prime, right? This is A. So A prime is A prime 0. So that means it's going to give me the same answer. So which means if you got A, B, so let me redraw this. There is an A and B, okay, and put it, you know, a MUX here. Now I'm going to connect this one to here, and then this one to here, and then this one to here, and I get an output. This will become AB. Okay, so I'm not even worried about having a 0 or a 1 in my circuit. I just connected A and B in an appropriate places, so I get an AB. Okay. Okay. Before final word, how about NOT gate? And let me discuss that. Can I get a NOT gate here? So you will have an input A, okay? And then you got an A prime. Can we get it? If I put A, 1, S to the A, and B, 0, you got the NOT gate, right? Is it too hard to see? So, let me just put it away. No, maybe it's late. I don't know. Okay, so I put A, so this is 1. B is 0, so this is 0. And I got SA. Maybe this A and that A is confusing yourself. Maybe, that's maybe why. And I put an S here, and I got an A prime. Okay? All right. Thank you very much. I think this should help you with the lab question. Please make sure that whatever that is asked to you, for example, in any Boolean expression, make sure that you make it resemble to this expression. Okay? Just make it resemble.